Hello, SWIC Earth Science students. Welcome to another recorded lecture. So this week we are going to be talking about volcanoes and igneous activity. This is chapter 6. Again, please make sure that you read the chapter. And I do also want to say a small update to grading. So I will now be dropping one lab score. This is because for the minerals and rocks labs, originally they were separate. Originally they were together. Now they're going to be separate. So you had 13 labs originally. Now you have 14 labs, but still only 13 are going to be graded. I'm also going to drop one of your mastering exercises and two of your reading quizzes. So it's a little bit to help you in case you have missed things. Again, I want to say labs are not allowed to be turned in late according to the syllabus. I sent an announcement before spring break. If you miss a lab and don't inform me of a reason and in advance, you will not be able to turn in late after spring break. I will be following the syllabus that says labs cannot be turned in late, so they are due at the following lab or exam. You can turn them in to other locations as well, such as my mailbox, or turn them into me at class, but I will not be accepting them late, such as, coming in the next lab and turning in two. That is not going to be accepted after spring break. So, volcanoes. I'm going to go over some of these terms again. We have seen some of these terms already, but I just want to have them out there for you. Magma, this is molten rock beneath the Earth's surface. Lava is molten rock above the Earth's surface. It's the exact same thing. They're both molten rock. It's just where is it located. A vent is a place on a volcano where the eruption will occur. So this is where the lava comes out. A fissure is a type of volcanic vent that is linear. Cone, dome, shield, stratovolcano, caldera. These are all types of volcanoes that we're going to look at today. A crater is the depression around the vent at the top of a volcano. They can be very, very large. In the case of an extremely large crater, they are called calderas. So this is a particularly large crater formed by the collapse of all sides of the volcano. So calderas shouldn't be confused with the type of volcano that is a caldera. A caldera volcano is an extremely large volcano that tends to have a caldera type crater. People will call very large craters calderas though, so it is a little bit confusing that the term is used for both a crater, a very large crater, and a type of volcano. I prefer to use it only for the type of volcano. More terms. Magma chamber. This is where the magma will collect beneath the volcano. There can be more than one magma chamber in a volcanic system. Magma evolution. So the first part of the magma to cool is going to be the composition that has the highest freezing or melting temperature. So basically, as the magma goes from extremely high temperature to lower temperatures, the things that melt at those high temperatures will no longer remain molten, and so they will solidify first. So this will end up changing the remaining composition of the magma. It tends to get more felsic because those things, if you remember from Bowen's reaction series, they have a high melting temperature are the more mafic materials. Crustal assimilation. So this is where we're going to incorporate melted crust into the magma. This tends to make the magma more felsic because the crust is felsic. Viscosity. This is how easily a fluid flows. Water has a low viscosity. Honey has a slightly higher viscosity. Peanut butter is very high. I have no idea why I always use food analogies, but I tend to do that. Maybe I'm always hungry. Volatiles. These are the dissolved gases that make the magma bubbly. So when we looked at our pumice as a rock last week, the volatiles are what make it have the air holes. Effusive eruption. I think this is the first one that you haven't actually seen. This is where you have a volatile pore eruption, and so you tend to have an outpouring of lava without a lot of spitting and, bubbling, and it's just flows. So think about Hawaii. That's an effusive eruption. And then pyroclastic, this is any sort of erupted materials. So this is the ash, this is the solid bits. So these are the materials that are then going to become the rocks that are basically sedimentary igneous rocks. So these are things like our tuffs, our pummices, our scorias, etc. I've already talked about all these words. I'm going to talk about these words again because they're important. So we have two types of volcanic rocks. We have well, technically three types. The ones that come from molten rock, we will have these two types. And then we have that third type, which are going to be the sedimentary igneous rocks that are also a type of extrusive rock, but they're a little bit different. So we have intrusive or plutonic rocks. These are the ones that are under the ground. This is the magma is intruding. It's pushing into the ground. This is magma that will cool beneath the ground. It has longer cooling times because it is cooling in a hotter environment. So it has the time to develop larger crystals. This is the phaneritic or visible crystal texture. The other type of volcanic rock is going to be our extrusive or volcanic rocks. These are lava that extrudes. Notice I said lava this time. It can also be magma that cools very near to the surface. The important thing here is that they have short cooling times. These are cooling in cooler environments, so they cool faster. Because they're cooling faster, there's no time for large crystals to develop, so we have very small crystals, or not visible crystals, the aphanitic texture. So what do we need for volcanoes? We need magma. So we have to melt rock. So we can do this in three ways. I talked about this during the Rocks Week. We can have what's called decompression melting. So decompression melting is where we're going to reduce the pressure, which means that we're going to reduce the temperature necessary to melt. If we bring rocks higher, so we bring them from depth where it's hot to a shallower depth where it's not as hot and has less pressure, if we do that fast, the rocks will still be hot. And that means that they will now be at the proper temperature for melting, and so they will melt. This is what we call decompression melting. We're reducing the pressure. This happens a lot at those mid-ocean ridges. It can also happen at hotspots. We can add volatiles. So adding volatiles is where we're adding those gases like water that will lower the melting temperature by breaking up the chemical bonds. So we're making it easier to melt the rock. Water coming off of the subducting slabs in subduction zones will lower the melting temperature of the plate above, which will allow those rocks to melt. Those rocks then will that magma will then rise to the surface because it's less dense, and so we get volcanoes off of trenches. And the final one is we can add heat. If you heat up a rock enough, it's going to melt. Now, for some of these rocks, that's a very, very high temperature, but if you heat anything enough, it will eventually melt. So this can happen in combination with the other two. So for example, when we have magma rising through crustal rock, it's going to melt the crust it comes in direct contact with. This also can happen at hotspots because a hotspot is defined as an area where you just have heat. So those are our three ways we can make magma, because magma is not found everywhere. We don't have volcanoes everywhere on the planet. They're only in these specific spots where we can create enough, have the right conditions to melt rock. So we have our four major magma types. I've already discussed this. You've seen this slide. We have felsic. That term comes from the feldspar and silica. It's the highest amount of silica. Intermediate, which is between felsic and mafic. Mafic is magnesium and iron rich. And then we have ultramafic, which has the least amount of silica. We tend to think about these as being light and dark. So the felsic materials tend to be lighter in color and they're lighter in density. The mafic materials and ultramafic materials tend to be made of darker materials and they're darker or higher in density. Not all magma is going to be created equal. Different chemistries will lead to very different volcanoes. So our more felsic materials, which is going to be our rhyolites and our granites, they are high in silica. That's why they're felsic. They don't have a lot of iron and magnesium. Again, that's why they're felsic. They have the lowest melting temperatures, but the highest viscosities, and they also tend to have very high volatiles. This means these are very explosive types of magmas. So this image is showing us the relationship of felsic to mafic. So towards the top we're more felsic, towards the bottom we're more mafic. The blue arrow is the silica content, so we have the highest silica content in the felsics. This red arrow is the melting temperature, so they are the lowest melting temperature. The mafics are the highest melting temperature. The green arrow is viscosity. Those felsic magmas are the highest viscosity. And then this orange arrow is volatiles. The felsic magmas tend to have the highest volatiles. So all these things combined together means that they tend to be extremely explosive. You have big eruptions with these type of volcanoes. Our intermediate compositions are andesite and diorite. The first word on all these is going to be your aphanitic rock. The second word will be your phaneritic rock, by the way. So andesite and diorite, there are intermediate magmas. They're called intermediate because they are mid-range silica. They are mid-range iron and magnesium. They are mid-range melting temperatures, mid-range viscosity, mid-range volatiles. They're right in the middle for everything. So intermediate just makes sense. These are somewhat explosive, so they're more explosive than, say, a mafic magma, but they don't have the, regional changing explosions that we can have with those more felsic materials. These do tend to have a traditional volcano type of material, though. So this final column over here is looking at our increasing explosivity. So an andesite and diorite is going to create what we typically think of as a volcano, that nice pointy mountain that periodically blows its top. The felsic compositions, our rhyolites and granites, are going to come from those large, what we call continental calderas. They change the landscape of a region when they erupt. Luckily, we don't have any current ones that do this. Our final type of volcano is going to be basalt and gabbro. So this is our mafic. I don't have ultramafic on here because ultramafic magmas can't make it to the surface, so they can't be volcanoes anymore. In order to be still liquid, they need such a high temperature that we cannot have them at the surface. So they don't make it to the surface anymore. They used to be able to, but they can't anymore because the Earth is too cool at the surface for them to still be fluid. So again, basalt and gabbro are mafics. They are low in silica, but they are high in iron and magnesium. Because of that, they have a high melting temperature, they have a low viscosity, and they have low volatiles. So they tend to flow very easily. They're not very explosive. So these are things like Hawaii. We call these shield volcanoes. We don't tend to have massive eruptions with these types of magmas. So depending on your chemistry, you're going to get a very different type of volcano. I will talk about all these volcano types throughout the lecture today. So these magmas will vary chemically due to, you may recognize this, we talked about this during the Rocks Week. What is the initial source rock? So the initial source rock is going to tell you what your basic chemistry available is. We can add in small amounts of different chemistries, but we're basically going to be limited by what we start off melting. That's a pretty basic concept. If you're trying to, if you have cookie dough and your cookie dough is chocolate chip, you're never going to get, snickerdoodle cookies out of that. So if you start off with like a sugar cookie dough, you can add things to it to change it to different things. But if you can only kind of get to certain variations from your initial. We can have partial melting and crystallization. So this is the idea of that as our magma evolves, as I talked about earlier today, that the chemistry will change. So if we solidify certain crystals and pull those out, that will change the remaining melt. Or if we have a solid and we're melting it, we pull out certain liquids first. And the final one is assimilation. So this is this idea of melting the rocks we're moving through and bringing them in and changing our chemistry slightly. Again, you've already seen these. So when we're melting rocks, the rocks will rarely dissolve completely. So the first things to melt will be the things with the lowest melting temperature, the easiest things to melt, which are going to be the more felsic materials. So the silica-rich materials will melt first. Those silica-poor materials are going to melt last. So the ultramafic materials will be the absolute last thing to melt because they have the highest melting temperature. So as we are melting a solid rock, the first things we pull out will be much higher in silica content, that will be more felsic. If we're able to remove that magma at that point, it will be enriched in the felsic components. If it remains in contact with the initial source rock and that source rock continues to melt, the magma will evolve to be more and more close to the source rock's actual composition. So it will become more and more mafic. Fractional crystallization is the same idea, only it's going in the other direction. So instead of taking a solid and we're pulling out the liquids, we're going to take the liquid and pull out the solids. So the first things to solidify will be the things with the highest melting temperature, because they can't remain melted if we start dropping the temperature. So this is called fractional crystallization. We're pulling out those first crystals. They tend to settle by gravity to the bottom of the magma chamber, which will leave the remaining melt more silica rich. So we're going to pull out the iron, magnesium, and calcium, the more mafic materials. The remaining melt will be enriched in the more felsic materials. So this will be the silica, the aluminum, the sodium, the potassium. So we can go from a mafic magma by pulling out those more mafic components to a more felsic magma. Both of these processes, actually all these processes, will drive our magmas toward the felsic end. And then assimilation is obviously, as we're moving through solid rock, we will melt that rock if we have molten rock in contact with it. When we're moving through the crust tends to be more felsic, so it has a lower melting temperature. So if we have a mafic magma moving through a felsic material, it will be hotter than the melting temperature of that material, so it can melt some of the rock it's in contact with and incorporate that. It will drive the melt to a more felsic composition. This explains why our continental magmas are so much more varied than the oceanic magmas, because we are moving through that continental crust that has all of that different chemistry. We can also have blocks of the wall rock, which are called xenoliths. Xeno means foreign, lith means rock, falling into the magma. And we call this assimilation. Every time I see this slide, I think about the dialects. That's a sci-fi joke. This will change the magma composition. So again, this is Bowen's reaction series, which is going to determine what melts or solids come out. So ultramafic and mafic materials have the highest melting temperature, which means they will be the last things to melt, but the first things to crystallize. So we pull those materials out first when we're crystallizing. They are the last things to be pulled into the magma. And then the felsic materials are the lowest melting temperatures, so they will be the first things to melt, but the last things to crystallize out. And again, we have these two sides because we have on this side plagioclase feldspar, which you saw in class. It has two compositional end members is what we call them. So it can be either calcium rich, which is more mafic, or sodium rich, which is more felsic. And as we move through temperatures, we will see a change in the proportions of calcium and sodium in that same mineral. So we're looking at one mineral on the continuous side. The discontinuous side, we're actually moving through different minerals. So olivine is just magnesium and iron and silica. Pyroxene has some other materials in there as well. Amphibole is that kitchen sink mineral. Biotite as well. So we're moving from different, more mafic minerals to more felsic minerals. Magma moves because it is fluid. So we will have the magma rise because it is less dense than the surrounding rock. The weight of the overlying rock also forms pressure, so it squeezes it up like a toothpaste tube. How easily this happens is going to be determined by the viscosity. Things that have low viscosity flow easily, so you don't create a lot of pressure. Things that have high viscosity don't want to flow, so you create lots of pressure. So the lower the viscosity eases the movement. So higher temperatures and lower silica content, which both indicate mafic magma, you will have easier flow. Higher volatiles will actually make magma less viscous as well, which, if you remember my slide a few back, I said that the felsic materials that are very eruptive tend to have high volatiles, but they have high viscosity as well. Volatiles make the magma less viscous, but they tend to escape our mafic magmas, so we don't have a lot in the mafic magmas. So that's not really the volatile content. While it will make things less viscous, if you have a high volatile content, it's not going to be enough to compensate for high silica and low temperatures. And we will see that, we do tend to have those higher volatile contents still in the felsic materials because they don't escape there as well. Whereas in the mafic materials, those volatile content tends to escape. So we tend not to have as much gas in those. So the volatile content is not going to be the determining factor for the eruption style. As magma cools, the rate and the chemistry is going to influence the type of rock. Again, the deeper a magma is cooling, the hotter the temperatures, therefore the slower the cooling, and so the larger the crystals. Shallower depths are are cooler, so that the cooling is going to be slower or faster. I'm saying this backwards. Deeper is hotter, so it will have a long time to cool, so we'll get big crystals. Shallow is cooler, so it will cool fast, so we'll get small crystals. So deep plutons lose their heat very slowly, so they take a long time to cool. Shallow flows will lose the heat more rapidly, so they'll cool quickly. The shape is also important. So spherical bodies, like what you would have a blob of magma at depth, will cool slower because you have the heat has to move through a larger distance, whereas tabular or flow-like bodies will cool faster because your heat can escape much faster because it's not moving as far. So if you have a flow on the surface, it's at a cooler temperature. It's also much less space for the heat to have to transmit through. So when you're cooking a cake, if you need it to cook fast, you put it in a flat sheet instead of a round because it will cook faster if it's spread out more. Smaller things also cook faster. Back to my food analogies. Groundwater can also help speed cooling because it can help circulate and remove heat. So this would happen again in the shallow. So ultimately shallow things cool very fast. Difference between lava and magma, we've already gone over this. Magma is beneath the ground, lava is above the ground, so your lava cake is not lava cake until you cut into it. Igneous rocks are going to be cooled from that melts, so the magma is melted rock below the ground. Lava is when it reaches the surface. The third type of igneous rocks are those tephra rocks, so these are the pyroclastic rocks. So this is material that has formed during explosive eruptions that's moving through the air and cooling in the air and then falling on the ground. So it's almost a sedimentary rock made out of igneous materials. This happens at high temperatures, depends on the composition. Again, the more mafic end will have higher temperatures, the felsic end has lower temperatures. And then you have these two settings. Extrusive settings will be near or at the surface. Extrudes, it's going exterior to the earth. They cool rapidly, smaller crystals, these are volcanic rocks. Intrusive settings will cool at depth, so it's intruding, it's inside the earth. It cools slowly, the crystals have a chance to grow large, so these are plutonic rocks. So, extrusive settings are volcanic settings. These are where we're going to have those effusive eruptions that flow without a lot of explosivity. So again, these are going to be our less viscous lavas that they can flow very easily. These tend to be the more mafic lavas. We can also have explosive eruptions at extrusive settings. So these are the tephra eruptions. They tend to be from the more higher viscosity that we're actually blowing material into the air, but we can have some tephra eruptions also with mafic, but this is the material that's cooling in the air and then falling on the ground. These tephra tends to be from the more high viscosity felsic magmas that erupt more explosively. That's what we're seeing over here. This is the material that will become the tephra, but you can get some also from mafic as well. Intrusive settings are going to be magma that invades a pre-existing wall rock. So it can either percolate up between grains, so it's pushing between the grains. We actually see that here. So here we have a granite that's intruding into looks like a basalt maybe, but this pinkish material, it has pushed its way between the grains. It can also force open cracks, so we are pushing between what once was a regular, a solid rock. So the intrusive features can be things like a dike. A dike is where it is going to be a vertical pushing up of material. We saw these when we looked at our age figures. You saw things labeled as dikes. This is what they are. So this is igneous material that has pushed its way vertically through the host rock. They can also then spread out sideways and become what's called a sill. So a dike will be vertical, a sill will be horizontal. So sills are igneous material that has pushed between layers. So dikes go across layers, sill will go between layers. The important thing about sills to think about is, was this material emplaced at depth, or is this going to be a flow? Because a flow would be an igneous eruption along the surface. The way that you're going to figure out whether or not you have a sill or a flow is going to be to use some of those principles of relative dating. So we're going to look at inclusions. Do we see pieces of the rocks on either side of the sill inside the sill? If we see pieces of the top rock and the bottom rock both in the sill, that means that those rocks were there first, so it is a sill. It's pushed its way in between those two layers. If we only see them on the bottom, well then that means it may be a flow, because if we're not seeing any of the top rock incorporated, that top rock might not have been there. It may have been deposited later. The other thing we can use is baked contacts or intrusion. So we're going to look to see, do we see alteration on either side of that sill? If this sill pushed its way between these two layers, it would have been fluid, it would have been molten when it did that. So it should have altered the layers on both sides. So it should have baked the contact. We should have slight metamorphism. If we only see it on the bottom, that tells us that it was a flow and that there was no top rock for it to push in between, that it just flowed out on the surface and the top rock was later deposited. So a sill and a flow, they will look very similar. We just have to determine, based on those two principles, inclusions and then baked contact or intrusion, whichever you want to call it, whether or not both the capping rock and the below rock were there when the material was emplaced, or if only the bottom material was there. We can also have plutons. This is basically just a big blob at depth. It doesn't have a specific shape. We call it massive. You will get dikes and sills off of plutons. You can also have then extrusive flows coming off of those as well. So in this block diagram, we see a large pluton, which is essentially a large magma chamber, and then we see some dikes coming off of it. Some of these are becoming actual volcanoes. We can have sills coming off those dikes. So these are all interrelated, and it's based on what the shape is. So this is what it would look like in real life. Here we have a pluton of granite. So when we're describing our igneous rocks, again, you've already seen this, we're going to look at the mineral composition. This will come from the magma composition, and we'll look at texture. So that's going to be the cooling history, and these two things will determine what word we use. So if it's an igneous composition, if it's felsic, we have it that's rich in silica. It has a lot of feldspars. It has a lot of granite. Not granite, it has a lot of silica, potassium, things like that. This is going to be the continental crust. It tends to be light colored and it's less dense. We have intermediate compositions, which is where we're having more of those mafic materials, but we still don't have a high percentage of mafic materials. Then we have mafic, which is the iron and magnesium. They are denser and darker colored. This is going to be the oceanic crust and volcanic islands. Ultramafic is almost entirely those dark, dense materials. Peridotite is the main constituent of the upper mantle. The ultramafic rocks are basically the mantle. The textures can be crystalline. These are the ones that are cooling from a molten material. It can be fragmental. These are the pyroclastic rocks, or it can be glassy, which is it's quenched. It is cooling immediately and doesn't have a chance to form any sort of crystals. Like there are glassy texture means there are no actual crystals in there. Crystalline textures are the one I focus on the most. So aphanitic are going to be the fine grained. So this tells you that you cool rapidly. These are extrusive rocks. The crystals don't have a time to grow, but there are still crystals in there. They're just only microscopic. Phaneritic is coarse grained. So this is a slower cooling. The crystals have time to grow. So this is an intrusive setting. The grains are similarly sized. So I want to take a note that the aphanitic texture is different from glassy texture because glassy has no crystals. Aphanitic still has crystals, you just can't see them with your naked eye. They're small crystals. Glassy does not have crystals. There are also other textures such as porphyritic texture. We saw this in lab. That's where you have two distinct mineral sizes. So you have larger grains embedded in a fine-grained, what we call matrix. The phenocrysts are what we call those large crystals. That tells us we had two stages of cooling. So we had slow cooling that would have started growing those larger crystals, and then we had that followed by rapid cooling that cooled off the background matrix. Okay. So for each of our crystalline textures, aphanitic and phaneritic, we have a rock type for each composition. So rhyolite is the aphanitic felsic rock type, granite is the phaneritic felsic rock type, andesite and diorite are intermediate rock types, and then basalt and gabbro are mafic. The ultramafic would be komatiite and peridotite. I showed you this chart before. I'm not going to walk all the way through it because I walked through it in the rocks lecture, but this is showing you again the silicic is the same as felsic, and this is showing you the aphanitic and porphyritic, and then the rock names for all of these. This side is showing us our temperatures, our densities, which we see both of those increase as we go to the more ultramafic, and then our silica content, which decreases. And then on this side we are seeing the percentages of the different chemical components, and then in this final column we see the actual minerals. This pinkish color would be our muscovite mica that just doesn't have a name, probably because it doesn't fit. And so we can basically see the evolution of Bowen's reaction series in this graph. I'm going to go through this part pretty fast because I already talked about all these. So ultramafic rocks, the only one we really see is peridotite. This is the phaneritic. This is what the mantle's made up of. It's primarily olivine with a little bit of pyroxene, but it's almost all olivine. Mafic rocks, we're going to see basalt and gabbro. This is what our oceanic crust is made of. We have more pyroxenes and calcium plagioclase in here. So these are going to be our low viscosity lava flows. So these are things like what we see in Hawaii. We have two types of lava flows we talk about. We have pohoihoi, which is the smooth, ropey texture. And then we have a'a, which is the blocky, crumbly texture. So the you will see these same textures in the same magma. It has to do with how they cool, the rate of cooling. It's not the chemistry. We can have an interesting formation called columnar jointing. This forms due to cooling. So these tend to have, this develops when the interior of a flow will cool and crack. So this one is Devil's Postpile in California. We like to give these things very interesting names. Volcanic rocks tend to get very, very interesting names. So columnar jointing is a very easy thing to recognize. It's rather distinctive. This is columnar jointing at the Giant's Causeway in Northern Ireland, which is one of the most famous columnar jointing examples. This is me. My sister and I were on vacation there. These are some of the columns. These are smaller columns, actually. They're farther around than I am. They are taller than me, obviously. These blocks are pieces of the columns that have broken off. These are all columns in the distance. So these are some, these are people. So this is a distant shot. These are large columns. This again is me next to some of these very large columns. So this is a zoom in of that same picture. I am obviously much smaller than these columns. And this is what happens when you ask your attorney sister to become your scale. My sister's 6 foot tall. So this column is about 3 foot across. This is looking across the middle of one of these. She can't reach all the way around it. So yeah, this was her response to me asking her to be my scale. She's like, do you want me to hug it? I'm like, if you want. Columnar jointing tends to happen in more mafic materials, but not always. We actually, very close to here, have an example of rhyolitic columnar jointing called the Devil's Honeycomb. It is at Hughes Mountain in southeastern Missouri. So it's rhyolitic columnar jointing. These are much smaller columns. These are, you can pick them up and carry them. I have several of examples of these. They aren't nearly as big, but they are quite impressive still. You can actually go hike to this if you want to drive down to southeastern Missouri and see it yourself. Mafic volcanic features continued. We can have a type of formation called a pillow lava. This happens when you have lava extruding into water. So basically you have this quick freezing of the outside and it's still somewhat molten in the middle, and it will insulate and it makes these, looks like they're pillows or bubbles. So these are examples on that have been scraped up onto the shoreline. This is what it looks like when it's actually happening. Here's another preserved set of pillows that have been cut through, and so we see the pillowy shape. We can have large scale features. These would be things called shield volcanoes. So a shield volcano is called that because it looks like a shield laying on the ground. So these happen when you have very low viscosity flows that can flow for long distances. So we have these eruptions that flow for very long distances. They don't have very steep sides, and so they're very large features. And so these are forming from successive flows. We have flow after flow after flow that are stacking up on top of each other. So this is what the Hawaiian volcanoes are. And then we can also have very large mafic features. So these are called large igneous profises, LIPs. These are unusually large outpourings of magma. They're also called flood basalts. So the Columbia River flood basalts would be an example of one of these. These are the things that I mentioned that will change the face of the Earth. Several mass extinctions in geologic histories have been due to these type of outpourings. These tend to be mafic. So this happens when we have a mantle plume first reaching the base of the lithosphere, and we have this large outpouring. So it erupts huge volumes of mafic magma as what we call flood basalts. Basalts because they're mafic, and they're cooling fast. Flood because there's massive outpourings of them. This is, the Washington area. The Columbia River flood basalts cover a good portion of a state. These will be low viscosity. They can flow tens to hundreds of kilometers. They will accumulate in very thick piles, and they again can change the face of the planet because they will change the weather patterns, climate patterns. So an example of an ancient one would be the Deccan traps in India. There are many examples of these. So here we see these large, thick outpourings of mafic material. That's the darker material in here. Intermediate rocks are going to be, again, our andesite and our diorite. These tend to happen on more of what we think of traditional volcanoes. So these are going to be the volcanoes that are happening like off the edge of subduction zones. So we can get a combination of flows and explosions. So our flows will not be as viscous, or I'm sorry, will be more viscous than our mafic, so they will not go as far, so they tend to be steeper sides. We also will have more explosive eruptions here, so we can have more of that tephra coming out. So we're going to have steeper sides and we're going to have more stuff thrown out. Our felsic materials are going to, again, be our rhyolites, granites, and obsidian is considered typically felsic. It is where we have no actual crystals. The high silica content of felsic materials leads to very viscous materials, so they tend to have extremely explosive eruptions. So back to this slide, the higher the silica, therefore the higher the viscosity, the more explosive we have. So we're going to have big booms with our felsic materials. And the lower the silica content, the lower the viscosity, the higher the melting temperature as well. We're going to have not very explosive eruptions with our mafic materials. There are different types of volcanoes. So these different types of volcanoes will be due to that chemistry. So stratovolcanoes are also called composite cones. They tend to be either andesitic or felsic. They have high silica contents. These are what we typically think of as being a volcano. They are cone-shaped. That shape is successive eruptions that do not flow very far, so they're very steep. And then we also have pyroclastic deposits, so where it blows its top. So we have lava flows and pyroclastic activity. So these are things, again, like Mount St. Helens, like Mount Fuji. These are the ones we think of as a typical volcano. We can have what's called a lava dome, which is going to be, again, andesitic to rhyolitic. So these are going to be intermediate to felsic. Their volatile content can be moderate. They form a dome, which is why they're called a dome. They have steep sides. These are outpourings of lavas that pile up near the vent of a larger volcano. They can be explosive, so they can form within another volcano. A shield volcano are going to be basalt, they're mafic, they have low volatile content. These are the things that are shaped like a shield. Our lava will travel very far, so these are Hawaiian volcanoes. A cinder cone tends to be more on the mafic side. They don't have a lot of volatiles. They are a steep-shaped cone that is formed from cinders or smaller bits of pyroclastic material. So these are tephra ejections. So these are things like SP crater in Arizona. They can form very quickly and also disappear very quickly. And then our large-scale volcanoes are continental calderas. These are going to be felsic in composition. They have a lot of volatile contents. They have a broad uplift, and they have a large summit depression. That is the, quote, caldera. They will blow everything. So they erupt tephra. These are things like Yellowstone. These are things that change the planet when they erupt. I will go through all of these again. So the eruptions are classified by the degree of explosivity. This is called the volcanic explosivity index. It goes from 0 to 8. They have different eruption types. So the eruption types are given names based on typical volcanoes that have that type of eruption. So like a Hawaiian eruption has a very low explosivity index. These happen at shield volcanoes. They're not very explosive at all. I've said this before and I will say this again. In the Earth, big things tend to happen not as frequently, which is a good thing, and small things happen very frequently. So we see that on this chart as well. So the lower the VEI, the more frequent they are. The higher the VEI, the less frequent. So things that are super volcanoes do not happen very frequently, which is a good thing. We have things that go to Strombolian, named after Stromboli in Italy. They are slightly more explosive than a Hawaiian eruption. They happen quite frequently as well. They do send material into the air. So the plume height is how high material goes into the air. So that's the thing that's concerning for like aviation. The reason we monitor volcanoes in remote areas is because if they send material into the air, that can disrupt our aviation, our flight paths. And that's what we mean by plume height. How high does it go up into the air? The bigger the eruption, the higher it goes in the air. For these really big eruptions, we are going tens of kilometers into the air. And that's up where our airplanes fly. Ejecta volume is how much material it throws out. So the bigger the eruptions, throw out more material. Let's see, we go from Strombolian to Vulcanian. Vulcanian is going to be more of a true, what we think of as a volcanic eruption. Pelean is named after Pele, the Hawaiian goddess of fire. We're starting to get to more eruptive. Plinian is named after Pliny the Younger, who described Pompeii. I'm sorry. Not Pompeii, Mount Vesuvius. I forgot about, it's written on here, Mount Vesuvius, which erupted in 79 CE or AD as the old term. And Mount Vesuvius destroyed Pompeii and Herculaneum when it erupted. Pliny the Younger described that eruption, so Plinian is referring to that type of an eruption. Ultraplinian is a little bit more extreme, and then supervolcanic is a supervolcano. This is where we're like blowing our tops. Luckily, again, these more explosive things don't happen as often, which is a good thing. So we can have some explosions even in these like Hawaiian type. We call these fire fountains. So this is where we have spitting basically before we have the lava just moving out. So it's spitting at the vent. And this is going to be only at the vent. It doesn't go very high. You can see in this image that this isn't coming up very, very high. Strombolian eruptions will have a stronger amount of this. So these tend to make like those cinder cones. So we have burps of lava at regular intervals. Stromboli erupts every 10 to 20 minutes. It shoots out what we call lapilli. So these are little cinders that come out. And so we see these arcs coming out. They look like kind of like fireworks. The material that comes out is going to be this tephra or this erupted material. So we get scoria, which are larger. We have large air holes. Lapilli are these little nut-sized things. Volcanic bombs are an actual large chunk of rock that comes out. So here's an example of a volcanic bomb. The smooth texture shows us this was partially molten as it was flying through the air. The shape also indicates that it was cooling as it was flying through the air. When these pile up, we make a cinder cone. So this is an example of a cinder cone. Felsic eruptions tend to have more of a plume. So this is where we have an eruptive column. So we're shooting stuff up into the air. So this is ash, soot, cinders. This is molten material that is like very, very small that's cooling rapidly through the air. So this, when it gets into an airplane engine, will remelt and it can, then have molten material in the airplane engine, but it's also shards. It can, really mess up your engines. So this is why we're very careful with aviation. We can also have what's called a pyroclastic flow in these more felsic eruptions. So this is where that material isn't just going up into the air. It then will move very, very fast down the side of the volcano. It's hot. It is only partially solidified and it's moving at extreme speeds. This will just blow out everything in its path. For Mount St. Helens, these pyroclastic flows were what destroyed most of the surrounding area. So felsic eruptions tend to have lighter materials because they're more felsic materials, lighter in color and in density. So here we have an example of pumice. Pumice will float. Tuff is these blocks of material made of ash, pumice, and other fragments that then basically, these are the sedimentary rocks that form from volcanic eruptions. So this is material that's settling out of the air and then falling and forming into rock. A crater is the depression at the top of a volcano. So this is where the volcano is blowing its top and it's blowing out a lot of the rocks. They can be very big, so they can be up to 500 meters across and 200 meters deep. So the more pressure that we're forming because we have stickier magma that's trying to get out, the bigger the crater is going to be. Again, these are our volcano types. I'm now going to go through the different volcano types. So the different volcano types are going to be very closely related to that chemistry. So the higher silica content means the steeper the sides tend to be. Stratovolcanoes are formed from those inner spaced layers of flows and pyroclastic eruptions. So we'll have a flow that doesn't go very far and is fairly steep because it's higher viscosity, it's higher silica content, and then we'll have pyroclastic eruptions between them. These are also called composite cones. So they're strato because of stratigraphy layers, or composite because we have this interspaced layers. So the large cone-shaped volcanoes, they have steep slopes made up of those alternating layers of felsic lava, tephra, and debris. They tend to be symmetric, although they can be odd-shaped because of landslides. So these are going to be examples of like Mount Fuji, Mount Rainier, Mount St. Helens, Mount Vesuvius. This is what we think of when we see a volcano or hear volcano. They're the typical volcano. These are going to be more explosive eruptions. Their magma chemistry will be intermediate to felsic, but you really can have all types of magmas for these. They're very common along subduction zones, so like the Ring of Fire. These are going to be Vulcanian through Plinian eruptions. And now I have a video talking about Mount St. Helens. So this is about 7.5 minutes.
The eruption of Mount St. Helens on May 18, 1980, was one of the most dramatic geologic moments in American history. It was a Sunday morning, 8:32 a.m. Vancouver, this is it, was the excited call on the radio from David A. Johnston to his colleagues. Within minutes, the colossal eruption had caused hundreds of millions of dollars in damage, and 57 lives were lost, including Dave Johnston. For 2 months prior to that eruption, scientists with the U.S. Geological Survey and the University of Washington's Pacific Northwest Seismographic Network had been closely monitoring the volcano.
All the deformation on the mountain was local to the mountain, and even more local than that was on the north side of the mountain only.
In the nearly 2-month period before May 18, what was essentially happening at Mount St. Helens was that magma or molten material was moving up from some deep reservoir beneath the mountain up into the volcano itself. And it began to grow or form what we call a dome or a cryptodome inside the volcano. And that inflating body of magma or molten material actually broke the north side of the volcano and began to cause the north side of the volcano to expand out toward the north.
We were measuring the rate of northward movement of the bulge at about 6 feet a day, and we knew that wasn't so good.
On the morning of May 18, I was driving up Interstate 5, headed up to the north side of Mount St. Helens with some parts and some batteries for our time-lapse cameras. And as I glanced over at Mount St. Helens, it was a beautiful blue sky day, and the mountain was sitting out there, and suddenly I saw this mushroom cloud go up above the volcano and climb rapidly up into the stratosphere.
When I was down in the room where the seismographs were at 8:32 in the morning, and I heard a sound, and I just looked over my shoulder, probably just a split second after the earthquake, the big earthquake had started, and saw that this was something very large, larger than we'd seen before. Watched it for a few seconds just to confirm that. And then I ran upstairs to the next floor, up to the radio desk of the Forest Service, and called Dave. And we couldn't get through. There was no answer.
So I guess I had the realization right away that this was some kind of a tragedy. And on the one hand, it was this huge, exciting, and interesting magmatic eruption, and on the other hand, I was pretty certain that something terrible had happened to Dave. So it was a strange day for me.
And we were off the ground probably at 9:05 or something like that. I mean, it was really, really rapid, and got up to the point where we could really see the mountain well, I suppose between 9:20 and 9:25, something like that. There was this terrific, very vigorous vertical eruption column There was the stem of the mushroom or the toadstool that then blossomed out at greater height. And for most of the morning, we saw this tremendous ash cloud roiling out toward the northwest. And I can only assume that that was coming off of the big pyroclastic flows that were going off in that direction that later built the pumice plain. It was a very eventful morning, but it was sobering because I remember thinking up in the airplane that Dave just couldn't have survived this, especially when we got around to the west side and saw all this ash headed in his direction.
On the morning of May 18, what actually happened, the landslide basically uncorked this pressurized body of magma and allowed it to explode or expand out towards the north very rapidly. This is what we call the lateral blast. It was a horizontally directed explosion of incredible magnitude. It caused this expanding cloud of ash, rocks, and gases to move out across the countryside to the north at speeds of several hundred miles an hour. The directed blast was really the most destructive event that occurred on the morning of May 18. It completely destroyed an area of 230 square miles in the matter of somewhere between 5 and 9 minutes. It essentially killed every living thing within an area of 230 square miles, and it destroyed hundreds of acres of virgin forest, and it was an incredibly spectacular event.
We put out news stations and we quickly started to remonitor the volcano again because we had no idea what was going to happen.
Before the dust had literally settled in the summer of 1980, there were USGS scientists swarming all over the area out in the blast zone, studying the pyroclastic flows, studying the debris avalanche deposit, studying the directed blast deposit.
We thought it likely that there would be more eruptions during the summer, and indeed that took place.
And suddenly this immense black eruption cloud came pouring up out of the white layer that the cloud tops. And I couldn't believe my eyes. I mean, I thought this is the most incredible thing I've ever seen in my life.
We learned a lot about how you interact with the civil defense, with the public, with the press. And that was transferred by the press to the world. And as a result, I think volcanology took a quantum leap in science as well as applicability to society's needs.
The subsequent eruptions were actually, most of them were forecast fairly accurately by the USGS team of scientists. So when it looked like another explosion was about to take place, our helicopter crews would pick us up and we'd move out to the outskirts of the blast zone. We'd watch and photograph the next eruption. As soon as the eruption stopped, we'd race out there and study the deposits while they were still hot, while they were just after they'd settled onto the ground. So it turned out that the 6 years that Mount St. Helens was erupting in the early 1980s was an unprecedented opportunity for USGS scientists to study hot, fresh, young, and exciting deposits from explosive volcanism. We learned incredibly new and important bits of information about how volcanoes like Mount St. Helens work, what kinds of deposits are produced during these explosive eruptions, and how to anticipate and mitigate the consequences of explosive eruptions.
Okay, so that's an example of how volcanology is, we study volcanoes during active eruptions, but also how it's important for the public. We can also have lava domes. These are going to be more felsic viscous magmas. They are small with low to medium volatile content. They tend to form in a larger edifice, a larger volcano. They can grow and collapse. I'm going to show you a video from a helicopter. This is Cleveland Volcano in the Aleutian Islands. There's a small lava dome inside the crater. That noise that you hear is the helicopter noise. I was not on this. This is someone else's video. I didn't get to fly up to the crater, unfortunately. So in here, this is our lava dome that is forming. So there is a bulge basically inside this crater. You don't actually see liquid, lava inside a crater. that you saw a little bit of heat there. So let's see if I can, I'm going to go back so we can show this again. And that material coming off is not just steam, that's also gases coming off, so it's very hot in there. So down in this lower corner you see a bit of red stuff that indicates that there's hot material down there. But yeah, so this dark in the middle is our lava dome that is forming. Shield volcanoes tend to be more mafic. This is places like Hawaii. They have low volatiles and low viscosity, so the shape is going to be due to this low viscosity of the magma, so it can flow for great distances. Hawaii is constantly getting bigger with every eruption, or the big island of Hawaii is constantly getting bigger with every eruption as that lava flows to the sea. The craters can be large enough to be called calderas in some cases. I prefer the term crater though for, to lower confusion. So we can also have fissure eruptions. This is what happens on Iceland, where it's that linear feature like what we see here. Recently, the 2018, I think, is when they started. Hawaiian eruptions were fissure-style eruptions. So I now have a video about the Hawaiian eruptions. So this is a little under 7 minutes long. So this is the talking about the recent eruptions, not even that recent, the eruptions in the past couple years on Hawaii.
Over the past 10 years, Kilauea volcano has erupted in two places, the summit and Pu'u'o'o. On April 17, 2018, USGS scientists observed increased pressure of the magma system beneath Pu'u'o'o. This caused the crater floor of Pu'u'o'o to rise. Kilauea's summit also went through a period of increased inflation. On April 26th, the lava lake overflowed onto Halema'uma'u crater floor at the summit. On April 30th, the crater floor of Pu'u'o'o collapsed. Two days after the collapse of Pu'u'o'o, the summit lava lake began to drop. After the collapse of Pu'u'o'o, USGS scientists detected a series of earthquakes moving east, signaling an intrusion of magma along the middle and lower East Rift Zone. The first fissure opened along the lower East Rift Zone in a residential subdivision called Leilani Estates. Between May 3rd and May 6th, 10 fissures opened in the lower East Rift Zone. By May 15th, the number of fissures increased to 20. On May 19th, lava flow fronts formed and moved towards the ocean to the southeast. On May 29th, vigorous lava flows from Fissure 8 began to move northeast towards Kapoho Bay. Over the next month, lava from Fissure 8 continued to flow towards the ocean, creating a large lava delta. This delta and other ocean entries created about 875 acres of new land. As the summit subsided and adjusted to withdrawal of magma, powerful earthquakes and ash explosions grew more frequent. The largest earthquake was magnitude 6.9 on May 4th at 12:32 p.m. The largest ash plume rose 30,000 feet above sea level on May 17th at 4:17 a.m. By June, the caldera floor began to rapidly collapse. Dramatically changing the summit landscape throughout June and July. From May through August, more than 80,000 earthquakes rocked the summit with 62 major collapse explosions. As a result, the depth of Halemaumau crater increased from 280 feet to approximately 1,600 feet, and the diameter more than doubled. By early August, the volume of lava erupting from Fissure 8 began to decrease, and the earthquakes at the summit grew less frequent. Even though the eruption events shown in this video appear to have slowed, it is difficult to know if they have ended. As of September 2018, lava flows covered 13.7 square miles of land. Over 700 homes have been destroyed, and approximately 2,000 people have been displaced. Many places within Hawaii Volcanoes National Park are transformed by these events. Hawaii Volcanoes National Park thanks all residents and visitors of Hawaii for their continued cooperation and understanding as the park continues to recover.
So that particular eruption is over. There has been another smaller eruption since then, but that particular one is over. This video was created towards the end of the eruption. Cinder cones. These are small. They're formed of eruptive tephra or scoria or cinders. They grow very quickly. They can also disappear very quickly. So these tend to be more mafic magmas with medium volatile content, so they are more explosive. So they will eject, cool, and fall, forming those edges. They also can be called scoria cones. These are more Strombolian type. They're slightly more explosive than Hawaiian type of eruptions, which is why we have that tephra coming out. Calderas are going to be the most explosive of our volcanoes. So a caldera is a gigantic volcanic depression. A continental caldera eruption is when you have one of these regional volcanoes that blows. A caldera is going to be much larger than a regular crater. It's tens of kilometers across. They form when a magma chamber empties and the volcano collapses into that evacuated space. They're going to be typified by steep-sided walls and flat floors. So examples of these would be like Crater Lake in Oregon, which is not actually a crater, it's a caldera, and Yellowstone National Park. When you drive into Yellowstone, you're actually driving up the edge of the caldera. So basically we have this massive magma chamber, it completely empties, and then there's now this void that the above volcano will collapse down into. So Crater Lake, Oregon is actually a caldera, not a crater. And then Wizard Island in the middle is a smaller volcano that protrudes from the lava. It grew up on top of the caldera floor. So So these continental calderas, such as Yellowstone, are the collapse of the volcanic edifice due to emptying out that magma chamber. It's not a passive process, so basically we inflate as we empty out, and then we deflate. These are going to be ultraplinian to supervolcanic. Tambora 1815, the year without a summer, is an example of an ultraplinian. It's not a true continental caldera. It was just a very large stratovolcano. That is the closest that we have in recorded history for one of these events. Things like Yellowstone erupt on the order of tens to hundreds of thousands of years, which again is a good thing. Flood basalts. We have no modern examples of active flood basalts. Also a good thing. This is where we have that massive outpouring of mafic lava in the past. These are major events. They tend to lead to mass extinctions. So again, these large igneous provinces, they're mostly mafic. The mantle plumes will first reach the base of the lithosphere, and then we have this massive outpouring of mafic magma as flood basalts. Low viscosity, they flow tens to hundreds of kilometers. They will accumulate in thick piles, like the Deccan traps. We can have other basaltic eruptions. So if magma comes in contact with water, we call this a phreatic or phreomagmatic eruption. It gets extremely energetic. Remember, water is one of those volatiles. Volatiles make things more explosive. We can have Vulcanian eruptions. A Vulcanian eruption is a short, violent, but relatively small eruption of viscous magma. It results from the fragmentation and explosion of a plug of lava in a volcanic conduit, or the rupture of a lava dome. These are other types of eruptions. So I've been talking about the different energy of these explosions. What about the sizes? So volcanoes are a little bit deceptive in their sizes. So we think about things like Mount Rainier as being a really big volcano. Mount Rainier is a fairly large stratovolcano, but it's tiny when you compare it to other types of volcanoes. So down here in this lower image, I'm showing you a stratovolcano, Mount Rainier, which is a larger stratovolcano compared to a couple of shield volcanoes. So we have Kilauea and Mauna Loa. Mauna Loa is more than 120 miles across. Mount Rainier is fairly tiny compared to that. A cinder cone would not even be visible on this image. Cinder cones are found on the sides of these stratovolcanoes, so we wouldn't even be able to see it. Like this dark bit would be like a cinder cone. Actually, that dark bit would be bigger than a cinder cone. So shield volcanoes are massive compared to stratovolcanoes. Stratovolcanoes are massive compared to cinder cones, but nothing compares to these continental calderas. So Yellowstone is shown here in this red bit. Yellowstone is big enough to cross state boundaries. The materials that erupt out of Yellowstone are shown in this triangle here. We also have Long Valley Caldera, which is showing this smaller blurb. And then we have Mount St. Helens up here, and we're seeing the extent of the ash from the 1980 eruption. So Mount St. Helens ash made it all the way across the state of Washington into Idaho. Okay. Yellowstone, when it erupted 640,000 years ago, covered basically all of the central U.S. This is what can change the climate when we have these types of eruptions, and it does. Which is why it's good they don't happen very often. They happen on the order of hundreds of thousands of years. So again, here's the explosivity index. These are the the smaller eruptions tend to not be as violent, and they tend to happen more frequently. The larger eruptions are extremely violent, and they happen very infrequently. Regions at risk. In the U.S., Alaska, the Aleutian Islands are all volcanoes. The Pacific Northwest, subduction zone. California has actually a lot of volcanoes as well, and Hawaii is, well, a hotspot volcano. And then Yellowstone. If Yellowstone goes, the entire country is just, we're in trouble. Actually, most of the planet's in trouble. For the rest of the globe, the Ring of Fire, all those subduction zones are volcanoes. Japan is also subduction zone volcanoes. Any subduction zone is at risk of volcanoes. We also see volcanoes in rifts, so the East African Rift has a lot of volcanoes. Volcanoes are actually found everywhere, even in Antarctica. That's what a lot of my graduate work was about. They happen wherever we find that magma. So they're all over the globe, but in specific places in the globe. So here, we are seeing, if you count up the number of volcanoes per country, the country that has actually the most volcanoes is the US. Why? Because of the Aleutian Islands. So that video I showed you of the volcanic dome is here at Cleveland. One of these just had a high alert recently. Which one was it? I don't see it labeled on here. One of these had a high alert recently, and I'm not seeing. Oh, Tanaga had a high alert recently, in 2023. So these, the Aleutian Island volcanoes are very important because they impact the Pacific Ocean aviation. So we are very concerned about those. Hawaii, obviously, these are all volcanoes. Extinct volcanoes in the case of the ones away from the hotspot, but these are formed from volcanic events. And then we actually have subduction up here in the Pacific Northwest, and then we have Yellowstone is a hotspot, and we have we have volcanoes also in California. So if we look at the rest of the U.S., we see, again, lots of volcanoes all along. We call it the Ring of Fire around the Pacific Ocean because of all these subduction zones and all the volcanoes. We see a lot of volcanoes in the East African Rift. We see volcanoes along any mid-ocean ridge as well. So we do see volcanoes everywhere. We also have intraplate volcanoes. Just like we had intraplate earthquakes, we have intraplate volcanoes. These are hotspots. So Hawaii is the most famous hotspot. I already talked about them. I'm not going to go into them in a lot of detail. But this is going to be a volcano caused by a temperature anomaly. So we have this, we call it a mantle plume. This is hot area coming up from the mantle that's in the middle of a plate. It causes melting. We then get a volcano. That hot area remains stationary and the plate moves over top of it. So we can track our plate motion by looking at hotspots. I already discussed this figure in depth. I'm not going to do it again. I just want you to see it. We can also have, once we're away from that hotspot, we will see changes in the landforms. So these are called atolls. So we start off with a volcanic island. That volcanic island will typically develop a reef around it. So that's what we're seeing here, that this reef will develop around the island. If that volcano is no longer growing, if it's not connected to the magma source anymore, it will, if it's not actively growing, it will start to erode. It will start to be broken down by surface processes. So it will get smaller. It will subside. So the volcano will get smaller. That reef will still be there though, so we will form what's called a lagoon. So it's a protected area of water within the reef. Eventually, that volcano will no longer be a volcano, it will become a seamount. It will go beneath the oceanic surface, and that ring will still remain there, and that's what we call an atoll, where we have this ring of reefs that's protecting a lagoon. There may still be a small amount of land visible, but there may be no land visible at all. So this is an example of an atoll in French Polynesia. So we have our surrounding reef that gives us our sheltered area of lagoon, and we have our subsiding volcano in the center. Are they actually caused by deep-seated mantle plumes? There's a lot of debate on these. Where is the plume coming from? How many are there? There's still a lot of research going into this. This figure has a suspiciously large number of hotspots listed on it. Some hotspots are not debated at all. Hawaii, for example, is not debated at all. These ones that show the same motion are probably not debated. This one has Cameroon as a hotspot. Cameroon's not a hotspot. They are wrong about that. This one here is not a hotspot. This is from the rift. So they do have, this figure is ambitious in stating hotspots. But there are multiple hotspots. The Hawaiian one's the most famous. Volcanic eruptions happen rather frequently. So here are some rather famous ones. Mount Vesuvius destroyed Pompeii and Herculaneum. Tambora in 1815 caused global cooling. 10,000 people were killed by the volcano, but additional 80,000 starved. It produced the year without a summer. Krakatoa was a tremendous explosion, more than 36,000 deaths from a tsunami. Le Soufre in Mount St. Helen or in St. Vincent, killed 2,000 people. It caused the extinction of a tribe. Let's see here. There have been several massive eruptions out of Iceland. In 2010, there was a large ash eruption from Iceland that disrupted air travel across the Atlantic Ocean. Let's see, Mount Pinatubo in 1991, it caused a typhoon. It killed more than 740 people. Many people were evacuated. That one also led to cooling for, I think, 2 years. Montserrat in the Caribbean in 1995 basically changed the island. So we have these rather frequently. So they can be extremely disruptive. We also learn a lot from all of these eruptions. So there are 50 to 60 eruptions per year. Aside from Kilauea, this is a slightly old statistic, Kilauea had been continuously erupting since 1983. That 2018 eruption actually changed its eruptive style slightly, so it's not truly continuously erupting anymore. There are 2 to 3 in the U.S. They're mostly in the Aleutian Islands of Alaska. About 500 million people live near volcanoes. People like volcanoes. They're good for farming. The soil is very, very fertile. It's also beautiful. So a lot of people live in the path of destruction. Over 100,000 people have been killed over the past century by volcanoes. There are a lot of hazards associated with volcanoes. So you have the actual eruptions, the lava flows, the pyroclastic activity. We also have gases. Gases are important for the evolution of the planet, but they can be dangerous. We can have a specific type of event called a lahar. We'll learn more about movements of materials next week, but a lahar is a specific type of movement of earth materials due to a volcano. And then we can have tsunamis. So a tsunami, we already learned about tsunamis, but if you have that material going into the water, it can generate a tsunami. So the lava flows are obviously where you have the molten material moving across the surface. Pahoehoe is the smooth lava that we see up in this upper image. I didn't have the emphasis on these because I can't find them on my keyboard ever. Is the more blocky one. An actual flowing lava is fairly easy to get away from if you're aware of your surroundings. That doesn't move all that fast. We can also have, one of the dangers of lava flows though are that it can insulate itself. So you can have a shell of what appears to be solid material with molten material underneath it, and we call these lava tubes. So basically we will form rock that then insulates and allows the molten material to remain hot longer, and it allows it to move further. And that can be dangerous because you can get these bridges that may not be very stable. Pyroclastic activity are the ejected materials. So this is the tephra and the ash falls. They can bury buildings. They're dangerous to airplane engines. So the glass shards can get reheated. They can also damage propellers. We can have pyroclastic flows, which are again those fast-moving clouds of hot debris. And we can have lateral blasts. So we can actually have eruptions coming out the side of the volcano that is extremely directed. That's what we saw with Mount St. Helens. So these images are showing us ash flows. We're seeing the eruptive actual column and then the pyroclastic flow, which moves extremely fast. This image is showing us the death cast from Pompeii. So these are the when Mount Vesuvius erupted, the ash. Luckily, these people probably died from gases before they were buried in hot ash, but their bodies were buried in hot ash. They likely suffocated from the gases. I don't know which would be the better death. That hot ash then solidified around their bodies. Their bodies decayed away or melted, burned away. When Pompeii was rediscovered, these cavities were found, and an inquisitive archaeologist put plaster Paris into these cavities, and it turned out that these were where bodies had lain. And so we have a death cast of the population of Pompeii. It's extremely haunting to see these. Gases are the silent danger. So these are going to be things like carbon monoxide, which is obviously very dangerous. Carbon dioxide, which can also be dangerous if concentrated. Hydrogen sulfide, water. Water's not dangerous. I'm not SO2. What is SO2? I'm trying to remember what SO2 is. Water and carbon dioxide make up the most, but not terribly dangerous gases. The others can be dangerous if concentrated. Some of them are just toxic, but mostly it has to do with the concentration. So these gases tend to be denser than oxygen. We need oxygen to breathe. So what happens is if you concentrate these gases and they displace the oxygen we need to breathe, people can suffocate. People and animals can suffocate. So an example of this is the Lake Nyos disaster in Cameroon. Cameroon is in Western Africa. Mount Cameroon is an active volcano. So in the 80s, this happened. And Mount Cameroon last erupted around like 2000, I believe. But so what happened is there is Lake Nyos, which is a lake up on the side of the volcano. There was gas collecting at the bottom of the lake. So volcanoes constantly release gas even when they're not actively erupting. So these volcanic gases, mostly carbon dioxide, were collecting at the bottom of this lake. That was fine until the lake overturned. So the lake overturned in a natural process where we had density contrast, and so the material at the top displaced and moved to the bottom, became more dense and moved to the bottom, which displaced the material at the bottom. When the material at the bottom came up, it brought those dense gases with it. Lake Nyos was higher up on the side of the volcano. Those dense gases were then released and they moved down the volcano because they were more dense into a valley that had several villages, displaced all the oxygen and asphyxiated every living thing basically in those villages. So it kills people and livestock. This is what we mean by a silent danger. There wasn't an active eruption. There was no indication of an active eruption. This is a passive process. So now Lake Nyos has pumps in it that release the gases continuously, so it can't collect because it was that collection, that concentration of the gas that was dangerous. So this is something that many volcanoes are monitored for constantly to make sure that this type of thing doesn't happen again. Also, changes in gas concentrations can indicate changes in what's happening within the volcano itself. Lahars. So this is an Indonesian word for, it's a debris flow or a mud flow. So basically we have a combination of water with volcanic ash that will lead to this massive movement of materials down slopes. They're especially dangerous on volcanoes with glaciers because the glacier is frozen water. So if you have frozen water on top of a volcano and that water gets heated up, well, suddenly you have liquid water. And it will combine with all of those volcanic materials to make this very fast-moving mud flow that is extremely dangerous and will wipe out everything in its path. There are other natural hazards. So earthquakes are produced by magma movement. The earthquakes actually help us monitor volcanoes. Lightning is often seen during eruptions from the interaction of the ash particles in the air. Fires, obviously you have molten rock, so it's extremely hot, so it will burn anything it comes in contact with. Landslides are quite common. We are moving this material beneath the earth, which can disrupt the material on top of the earth. The landslide off of a volcano can trigger a tsunami. So the December 2018 tsunami was caused by material from a volcanic eruption going into the ocean. We can also have global cooling after large eruptions. The ash will block out solar radiation. So this bottom image is shown as Mount Pinatubo's eruption. This caused global cooling for about 2 years after the 1991 eruption. This is a fast video just showing volcanic lightning because it's just cool. So this is lightning during volcanic eruptions. I believe this is, Philippines. So again, you have these charged particles that are interacting with each other and produces this very impressive lightning. So the more violent the eruptive cloud, the more impressive the lightning is likely to be.
Hey, thanks for watching.
Okay. Is good that can come from volcanoes. So volcanic soils are extremely fertile. This is why so many people live on volcanoes. We can also get geothermal energy. So a lot of hot springs are due to volcanic activity. We have mineral resources. There's a lot of important minerals that come out of volcanoes. Tourism. People love to go visit volcanoes. Sometimes it's not a good thing. We create new land. So the reason we have Hawaii and it's getting bigger is because of volcanic eruptions. Volcanoes were also very important for the early Earth. Volcanic eruptions is what helped evolve our atmosphere. So there's a lot of good that comes out of volcanoes. Speaking of the tourism, we have tourism from modern volcanoes, tourism from old volcanoes. So this columnar jointing that I would love to go back to, this is tourism. Humans and volcanoes. We can't stop them. All we can do is monitor them. So we keep an eye on them. All volcanoes are unique. They do tend to have the same general processes, so it's important to study volcanoes in general and then to understand the specific volcano to know what its pattern is. So we have to study each volcano before we can try to, quote, forecast. The precursors, the before events, will vary between volcanoes. So we don't always recognize our precursors. So some volcanoes will have a decrease in seismic activity before eruptions. Some volcanoes will have an increase. Sometimes you don't notice that until after you've had an eruption. You go back and look at the record and say, oh, there was a slight uptick. So one of the key ways to monitor is seismic. We see the movement of magma through movements of the earth through seismic waves. Again, we also tend to see these reductions in seismic activity in many volcanoes. Increases in seismic activity in many volcanoes before events. So we see that here. That when we look, we see these increasing numbers of events, and then we'll see, oh, we had an eruption. Increasing number of events, oh, we have an eruption. There are specific volcanoes that will slow their seismic activity. They go into what's called quiescence. It's not the common pattern, but there are certain ones that show that. And again, we can also track the magma movement. That happens a lot, especially in Hawaii and Iceland, where they have nice monitoring. They can actually track how the magma is moving. We can look at thermal signals, so is it heating up? Magnetic signals, hydrologic conditions, is the groundwater changing? We can look at the deformation. Do we see a bulge forming? So we can use that using tilt meters. So do we see a change in the shape, or GPS, is it moving? Gases can change near eruptions. We also want to always monitor for toxic levels of gases. And then the important thing is look at the history of the volcano. So how often has it erupted in the past? What is the frequency of those eruptions? So we will try to determine the past behavior in order to figure out what the potential future behavior will be. It's important to also talk to the public, so we alert the public when activity changes. So the USGS monitors the majority of US volcanoes, not all of them, but the majority of them. They send out weekly updates, and you can go to the USGS website and sign up for these updates. They have two alert codes, so they have what they call the ground alert, so that's either normal, advisory, watch, or warning, and then they have the aviation, which is a color code. So when there's an increase in potential activity, those codes will go up, and then they will go back down. There are certain volcanoes that always live in the advisory or the yellow, that there's always that potential. Many of our volcanoes live in the normal and the green. You can see these. We do have observatories. The U.S. observatories are AVO, the Alaska Volcano Observatory. We have a California Volcano Observatory. We have Cascades Volcano Observatory, Hawaii Volcano Observatory, and Yellowstone Volcano Observatory. Other countries also have their own observatories. You can go to these websites and you can go and look and see what are happening at these different websites. I particularly love AVO's website. You can go look at webcams that they have installed on many of the volcanoes and see what's actively happening. If the weather's good, they will tell you what the alerts are. You can sign up for different alerts. They also have links to the other observatories. AVO and HVO, Hawaii and Alaska, are probably the most active with monitoring because those are where we have the most activity. Cascades, luckily we don't have a lot of activity there. They do a lot of research though, but they are constantly monitoring the Cascades. Those are the ones in the Pacific Northwest. Yellowstone and California are kind of built into some of the other observatories, which again are more of the research. So what can we do? Lots of people decide to live on volcanoes. They may have no choice. They may be optimistic, thinking it can't happen here, or they just want to live in paradise, like in Hawaii. Insurance is not always available. In fact, many places will not insure you if you live in a volcano. So you can try to control it. These aren't very successful. Hydraulic cooling, so they try to cool the lava down. Doesn't work very well. We're talking about molten rock. It takes a lot to cool that down. Trying to construct walls to redirect lava. Again, it's molten rock. You have to have something that's very, very temperature resistant in order to not melt from the molten rock. So trying to control a volcano doesn't happen very easily. It's better to understand the volcano and be ready to get out of its way. And volcanoes are probably the most common natural disaster in Hollywood. I love making fun of volcanoes in movies in Hollywood because they're bad. They're always bad. They always use the stratovolcano shape. So Dante's Peak, Jurassic World, Mount Doom. Volcano, the movie Volcano with Tommy Lee Jones, is one of the notable exceptions. It's not a stratovolcano. They always have low viscosity flows. You see the lava flowing. But, as we just learned, stratovolcanoes tend not to have low viscosity flows. People get very near to those low viscosity flows. Remember, that's going to be the high temperature lava, without feeling it. So, Jurassic World, he hides behind a tree to save himself from the lava. People will drive through lava. Dante's Peak, they do that. The only thing that happens is their tires catch on fire. People drop buildings to redirect lava. That happens to Volcano. Volcano's got so many problems. Volcano, if you want to see a bad volcano movie, that's probably the best bad volcano movie of recent ones. I have to keep talking about the Jurassic World when he hides behind a tree to try to save himself from the lava. It's ridiculous. Once you understand volcanoes, it is rather enjoyable to watch some of these movies and make fun of them. I love Lord of the Rings. I adore it. When we get to Mount Doom, I get so upset. I get so mad at Mount Doom because it's so wrong. Even though it's fantasy, it should still follow, physical laws of nature in my brain. So now that you have learned this, you can too enjoy that wondrous making fun of volcano movies. So in my original order of things, which may be changing up in future years, so if you're not watching this video in 2023, the following pre-lab video may be wrong. I'm going to show the pre-lab video for earthquakes and Earth's interior. If that is no longer the pre-lab video for this week's lab, go watch the right one. But now we are going to show the pre-lab video, which is 9 minutes long.
Hi there, this is Callan Bentley. Welcome back for another pre-lab video. This week in lab we're taking a look at earthquakes, and we're going to use earthquakes to actually take a look deep inside the earth where no person can ever go. Have you ever experienced an earthquake? They are pretty dramatic events, and after you've been shaken you might wonder where all that shaking came from. Well, the deal is this: when there's a fracture in the earth and stresses build up along that fracture, and those stresses are greater than the friction that's holding the fracture in place, then the blocks of rock on either side of the fracture slip relative to one another. This makes the fracture a fault. The spot where the fault slips is known as the hypocenter. Oftentimes in the news after a big earthquake, you'll hear a different term, and that is epicenter. Epicenter refers to the spot on Earth's surface directly above the hypocenter. Sometimes if the fault makes it all the way to Earth's surface, you'll get a fracture that actually shows up at the surface, and that's called a scarp. Now, seismic energy is transmitted through Earth's interior, and it comes in several flavors. Those are illustrated here in this diagram from your lab manual. You will notice that there are three types of seismic waves, or earthquake waves. The first of those is called a P wave. P waves are compressional waves. They're the very fastest of the different kinds of seismic waves. So they will always show up first, no matter how far away from the earthquake you are. Second is the S waves. S waves are also body waves, meaning that they travel through Earth's interior, just like P waves, but they're a little bit slower, so they show up second. And then lastly, there are the surface waves. Surface waves are the slowest of the earthquake waves, and they only travel along the surface. So they do not travel through Earth's interior. Let's take a look at these three different seismographs here. The first one basically shows that we have 2 minutes between when the earthquake happened and when the P wave arrived. Whereas with the second seismograph, you can see 3 minutes have elapsed between the earthquake and the arrival of the P wave. And down here with seismograph 3, we can see that there's a full 5 minutes that pass between those two events. You'll also notice that the S waves take longer to arrive the further away you are. In the first example, it takes another 3 minutes for the S waves to arrive. In the second example, it takes another 4 minutes. And here in the third example, we don't even know because the S waves haven't yet arrived. So that time, that proportion between the arrival of the P wave and the arrival of the S wave, that is really important for figuring out how far away the earthquake is. So this week in lab, you're going to be using the difference in arrival times between the first P wave and the first S wave to figure out how far away the earthquake is from 3 different locations. So the way this works is you look at the seismograph, you figure out when the P wave arrived, you figure out when the S wave arrived, and you do the math. So say the difference is 3 minutes between them. You use the scale, the vertical scale on this graph to measure out a distance that is 3 minutes tall, if you want to think of it that way. So a little scrap of paper, mark the distance from 0 to 3, and then slide that over between the S wave curve and the P wave curve till you find the spot where it fits exactly, perfectly snug, not too big, not too small. That amount of time correlates to a specific distance away from the earthquake's epicenter, and that's about 900 miles in the case of this 3-minute travel time. On the other hand, the further away you are, the more distance there's going to be between the P wave and the S wave. So let's consider an example where the difference in our arrival times is 6 minutes. So if we slide that over, we're going to see that it fits much more over toward the right side of the graph, and that's going to correlate to a distance of about 2,800 miles away from the earthquake's epicenter. If you aren't going to use miles and you'd rather use the metric system, you have that option as well. The distance in kilometers is shown up at the top of the graph. So here's what you can do with that distance information. You can use it to draw a circle, and the radius of that circle is going to correspond to the distance that you calculated. For instance, in this diagram, you can see the city of Montreal has a S minus P time that correlates to a distance of 8,400 kilometers away from the earthquake. So every point along this red circle is exactly 8,400 kilometers away from Montreal. And so the seismologist would know that the earthquake occurred somewhere along that line, along that circle. So then you got to go and match that up with data from 2 other seismographic stations. So let's take a look at Paris. It's 6,700 kilometers away from Paris. So Paris says the earthquake is going to be somewhere along this orange line. That orange line crosses our red line in this spot here and then in another spot on the other side of the world. And a third seismographic station, in this case Sao Paulo, Brazil, has a different distance to the earthquake. And in that case, that third circle intersects the other 2 circles at one location and one location only. That location is the epicenter of the earthquake. So the way this is going to work for you in lab is after you calculate what the difference is in the arrival time of the P waves and the S waves, you're going to translate that into a distance away from the earthquake's epicenter, and then you're going to plot that information on a map that looks like this. So for instance, let's say we had one seismographic station in Central America, and it gave us a radius that looked something like this. So we go ahead and draw a circle to match. Then we get another seismographic station maybe in northern South America, and that has another radius for another circle. You'll notice that that intersects our circle in 2 locations, so we know that the epicenter must be at one of those 2, and we just need a third seismograph to tell us which one it is. So let's pretend we go and consult one from the northeastern part of the United States, and that intersects our previous 2 circles in one spot and one spot only. In this case, in the western part of the island of Hispaniola in the country of Haiti. So that's where our epicenter would be for this particular earthquake. One thing you'll notice about this diagram that I didn't talk about is that all of the body waves, the P waves and the S waves, are traveling through the mantle only, and I didn't look at the complications that result when they go down to the core mantle boundary. There they can refract, which means they change the orientation that they're moving at, or they can bounce off the core mantle boundary. There are additional complications with Earth's inner layers. The actual pattern that seismic waves take on can be more complicated than just a simple curving path. It can look something like you see in this diagram here. These different paths tell us something about Earth's interior. They tell us that we live on a layered planet, and that our planet has a mantle, it has a crust that's on top of the mantle, and it has a core beneath the mantle, and that core has several components, a liquid outer core and a solid inner core. Those different components are illustrated here. You can see that the mantle basically goes down to a depth of about 2,900 kilometers, and then the outer core goes from there down to 5,150, and the middle of the planet's about 6,371 kilometers down. So we've got the inner core here, the outer core, which is liquid, and the mantle. If you zoom in on the mantle, you will find that there is a weak portion of the mantle called the asthenosphere, and then we have the upper mantle joined to the crust. That makes the lithosphere above that. This is another graph that you'll be using this week in lab to answer some questions. Basically, it's a similar cutaway of the planet, where you can see over here on the left side of the picture a typical cross-section through Earth's interior. And then the right side of the diagram is a graph, and that graph shows the velocity of P waves and the velocity of S waves as they travel through the different levels in Earth's interior. You can see here on these graphs that there are several big breaks. There's a big break, for instance, at the inner core, outer core boundary, a big break at the bottom of the mantle where it meets the outer core, and then you can see some other interesting little complications higher up in the mantle. Each tell us something about the quality of the rocks that we find at that level, the conditions that they're under, and how they're responding to those conditions. So you're going to answer some interpretive questions based on those. Well, good luck sussing out how these earthquakes can help us see into Earth's interior. I hope you enjoy the privileged view that you get this week in lab. Good luck.
So apologies for the Heidi barking there. Hopefully that wasn't too disruptive. But yeah, so that is all for volcanoes and volcanic materials. See you next time.